Okay, so for this class, we'll start with question 3, part 2, where we're trying to use the results obtained in 1, working backwards, of course, to find the power developed by the 50-volt source. So here, of course, we did a few calculations to find what I0 is. We also found the voltage drop across the 15 kilo ohm resistor. Now we want to work backwards to determine the power developed by the 50-volt power supply. So how do we do that? You see, the formula for power in a circuit, power is equals to voltage times current. This is how you calculate power, implying that for this element, for this source, if we wanted to find the power developed there, all we'll have to multiply is the voltage it is supplying, 50 volts, by the current it is supplying. So we need to understand what the current coming from there is. This would give us the power developed by that element. So this is what we're trying to get, the current coming from this side. We're trying to get the current that will be passing in this line coming this way. If we can get the current I there, then we can use it in the formula to get the power developed by the 50-volt power supply. So how do we do that? Well, we're working backwards. We already know what I0 is, the current coming to pass through the 15 kilo ohms. So use this current to get the current that went down here. Once we understand the current that went down here, we'll use these two to get the current that approached this junction. And then at this point, since we know the current that was going down here was 1 milliamp, again, we'll use this node here to understand the current that entered that junction. Once you reach this point, we can now also do a little bit of magic. Since we're working backwards, you see how to understand the current that went down this way. And once we know the current that went down to the 15, we can add these two to understand the current that was entering that junction. So this will be, we'll keep using Kirchhoff's current law. Kirchhoff's current law says that the sum of all currents entering a junction must be equals to 0. So this is what we'll be using throughout until when you're done with the problem. So I hope you have a rough idea of what we're going to do and how we're going to do it. So let's go to the problem. Since we're working backwards, this is the solution we had when we're getting I0. So we had this was the original circuit. Then we did a series of source transformations until when we obtained our I0 right here. So we obtained I0 using current division. So let's work backwards. Question 3. Going to be question 3, part 2. Okay, so working backwards, where are we starting from? Starting from here. From here, we know what I0 is. So I'll even be copying this as we go. So from here, we found out to say that the current that goes this side, that goes this way towards the 15 kilo ohms, we found this current as 15, no, sorry, that's the resistance, as 0.3 milliamps. Now, since the current coming from the supply here is 0.75, we can use that 0.75 to find the current that will go down here. So for this junction here, we can say at the junction, we use Kirchhoff's current law. At that junction, the sum of all currents equals to 0, implies that the 0.75 milliamps entering the junction minus whatever this is, let me just label it as I, minus that leaving the junction, minus 0.3 also leaving the junction. This must be equals to 0. In the end, the current that goes towards the 10 kilo ohms must just be 0.75 minus 0.3. When we do the math here, we see that the current that goes towards the 10 kilo ohms will be 0.3 there. That will be 0.4 milliamps. So we see that the current that will go down here will actually be 0.45. So that's the current that will go towards that 10 kilo ohms. Okay, that is done. Next up, so we found the current coming down towards the 10. But where is the 10 coming from? The 10 was a combination of the 20 kilo ohm resistor and the basically the two 20 kilo ohm resistors. The two 20 kilo ohm resistors were in parallel. So what we have done is, towards these two, we have seen that it's 0.45 that was going towards them. So look at them, they are in parallel. So if we were to reverse and see what was going to each one of them, if we were to see the current that was going to each one of them, how would we do it? Well, those two are in parallel. If the elements are in parallel, you have 20 here and you have 20 here. And then the current that is going to the combination of the two is 0.45 milliamps. Then to get how much goes to one, you're going to use current division. But because they have the same resistance, 2020, it just means that they will share this equally. So when the resistance here is the same, they'll share equally. But you can still try to use current division. You will see, I think we did use it at some point in the previous class, but it did end up bringing just half of one. So again, since they have the same resistance, they will share the current equally. Half of 0.45 will go towards that 20, half of it will go towards the one down. What am I saying? Let's get half of 0.45. That will be 0.225 milliamps. So this will imply that when we reverse to this circuit, so when we come to this one here, what we now end up with is the current I0 still 0.3 milliamps. But now the current coming towards this 20 kilo ohm resistor, 0.225 milliamps. And the current coming here, also 0.225 milliamps. Here, notice that you still satisfy Kirchhoff's current law. This being one node, if you added the currents here, they will still add up to 0. Entering that node, you have 0.75. Leaving the node, you have the 0.225, 0.225, and 0.3. So when you add these, you still end up with a 0. So we're still good there. Now, let's move backwards. Remember, I keep going backwards step by step. So let's take the next step. Let's reverse what we did. From here, the circuit was like this one. So let's reverse it to this form. So what changes in this form? You see, in this form, the current and that resistor were source transformed to a voltage in series with um, with a resistor there. So the voltage source in series with a resistor. But what does it change is the fact that I0, the current going this side, is 0.3 milliamps. But what doesn't change also is the fact that the current going this side, which is this one here, is still 0.225 milliamps. So this fact doesn't change. But this here, how much will be the current that will be coming towards this junction? How much will be the current? Don't make a mistake of getting this 0.225. That's not the current there. The current that will be going towards this point here will be the current that adds up to give you this and this. So if you use Kirchhoff's current law here, you understand how much current was approaching this junction. So if I label this current as I here, then Kirchhoff's current law there will be I entering the junction minus 0.225 milliamps leaving minus 0.3 milliamps leaving must give us 0. So I must be equal to 0.225 plus 0.3. When you add these, you get 0.525 as the amount of current that went this side. So when the circuit changes to become this, the amount of current that is coming towards this point, this current is 0.525 milliamps. So this is the current coming this side. With that done, what else changes? So let's see what came next. So I keep reversing one step at a time. So we're from this one, but that one came from this. So let's see what we already know. The current going this side, I0, 0.3 milliamps. The current going towards this 20 kilo ohms, 0.225. Excuse me. Then from this observation, we saw that the current passing here going this side, that was 0.525, meaning the current that was actually coming, did I skip one? Because here I have 20, and then now I have this one. Okay, I think we skipped one circuit where the 20 where these two combined to give us 20. I think I might have taken a shortcut for that one. But the way it was to move from this circuit to this circuit, it means that we source transformed to a voltage source and a resistor. When we had a voltage source and the resistor, the 15 and the 5 kilo ended up in series. That is how they added up to 20. So I hope, I think that's what we did there. It has to be. So it's just transformed from this current source and the resistor to a voltage source and the resistor. So the voltage source became 15 and the resistor was 15 as well. But the 15 and the 5 were now in series. So we added the 15 and the 5 to get this 20 kilo ohms. So that's the circuit which is missing there. But still, we can still understand it from here. Okay, I didn't have it there. So here, before moving to this one, we're saying this 20 kilo ohms was made up of two resistors, the 15 and the 5. So the current that passes through the 15 here is that 0.525 milliamps. So since this is the one that approaches this junction, coming towards this junction here, this is where you have the 5 kilo ohms. So the current that passes through the 5 kilo ohms, that current is what we are from finding, which is that 0.525 milliamps. So if this is how much current passes through the 5 kilo ohms, now the question is how much was coming this side and how much went down here. According to what we have here with the 1 milliamp supply currently, it implies that the current entering this junction is 1 milliamps. 1 milliamp enters. Leaving, we have the 0.525 leaving. Then here also we have something leaving. We don't know what exactly, so let's label it as I equals to 0. So that in the end, we end up with I goes to the right, becomes positive. We now have 1 minus 0.525. So we get 0.475. So this is how much current went down. And this side we have 1 milliamp. So again, let's reverse. So we are from sorting out this one here, and then now we're taking it back to this one. So just one step at a time, be patient with it, and then don't rush through. Okay, so we're now coming to this one. What have we done so far? Let's see. First, we have seen that this side, we have I0, 0.3 milliamps. Coming down here, you have 0.225 milliamps. And then coming through the 5, we have 0.525 milliamps. And then coming through the 15, it's the same one here, this 15, we have 0.475. So this is what we have here. Then next up, 1 milliohms. Yeah, so here we just combine these. In this step we just combine these. It doesn't change the fact that the current coming this side is 1 milliamp, and the current was split to give us 0.475 to go this way. So this doesn't change. Okay, so let's reverse one more step. From this one, which one? From this one, what did we have? We had this. So now I want to understand how much passed through that 15 kilo ohm resistor. And here we just swapped the resistors, the position of the resistor, but now we understand how much went towards this 15. So it's the same circuit. If you've noticed, I just reordered, we just rearranged. Yes, so when you compare this, the one on top and the one down, we just rearranged. But what doesn't change? What doesn't change is the fact that here, this is still 0.3 milliamps. Doesn't change the fact that the current coming down here is 0.225 milliamps. Also, the current going this way is still 0.525 milliamps. In the same way, it doesn't change the fact that the current that will still come and pass through this 15. Remember the 15, it's this one we just rearranged. From here to here, this is still one node. So how much current will still be the same? So this is still going to be 0.475 milliamps. Okay, so here we're just putting it here. Nothing changes as you move from that circuit to the last one there. Let's move a step backwards. So we are coming from this circuit. Now we're coming to this one. Remember the goal. The goal is to understand the current coming from here. So we're now coming to this part here. Okay, so we're now here. So let's put what is fact. This is 0.3 milliamps. This is 0.225 milliamps. This is 0.525 milliamps. And now, since the one going down here is 1 milliamp, want to know the current that is coming here, the one that split to give us 0.525 if what is going down here is 1 milliamp. Again, don't get confused to say that, okay, since what was passing here through the 15 is 0.475, to say that even here it must be 0.475. No, notice that here there's a contribution of this as well to the mix. So in other words, we want to know the effective current that will be passing through here coming towards this junction. That will not only be determined by this, it will be determined by a combination of this and the 2 milliamps there. But the easiest way to get it is just to look at current law at this junction. How much current I must be entering if what went this side is 0.525, and what came down is 1 milliamp. So for that junction, when we use Kirchhoff's current law, we have I entering minus 1 milliamp going downwards. Then we have minus 0.525 leaving the junction. Okay, yeah, that is equals to 0. So from here, we get I is equal to, we have 1 plus 0.525. So that in the end, I is going to be 1.525 milliamps. So we now understand the current that was going towards this junction. It had to be 1.525 milliamps. Okay, next up. Okay, so we now know how much current is passing through the 15 going this side. Let's reverse. When we come down here, we know the current that comes this side. Now the 15 was a combination of the 9 and the 6 down here. But does anything change here? Well, the current that comes this side to pass through this and pass through that, it's the same current. So if what is approaching this junction is 1.525, it implies that what passes through this is 1.525. What passes through that is also 1.525. Okay. And when we reverse them to the 9 being split to the 6 and the 3, it still means that the current, since this is series, it still means that the current that passes through the 3 is still 1.525. So that is where we are. We now understand the current passing through the 3. So with that, we can skip to this part here, this circuit here. We're almost going towards the last one. So we have just seen that the current passing through the 3 kilo ohms is 1.525. So I won't write all the others, I'll just come to the ones we are currently interested in. The one passing through the 3, we have just seen that this current will be 1.5. 0.25. That's the one that comes to split at this junction 2, so that we have 1 milliamp here and 0.4 and so on at the 5 kilo. Now we want to understand how much current went down here. So at that point, since what is coming here is 5 milliamps, Kirchhoff's current law, at that node, we're going to have the current we are looking for will be equal to 5 milliamps minus 1.525. I've just taken a shortcut there. Let's present it this way. So 3.475 milliamps. So here we have 475 milliamps. Okay, let's move back. So we're currently where are we? We're currently, is it here? Which is the last one from copying this one here. Okay, so for this one, we saw the current that is going this side. That was 1 point, I think 525. And then we also determined what was going down here. Now, when we reverse what we did, we determined the current that was going this side. That was the 3 point. But the current, you see, this resistor was obtained by combining the 10 and the 15. So we can split to see what went through the 15 and what went through the 10. Because those are in parallel, how did they share? So let's go back again. So we'll use current division to see how they shared. Okay, so we're saying that this 6 was a combination of the 10 and the 15. So to get the current, just the current that went towards the 15, you see, so the current that went towards the 15 here, just the 15, it's labeled I. In this case, the current towards the 15 will be the other resistor. So I'm using current division for these two resistors here to be the other resistor, which is 10 divided by the sum, 10 plus 15, multiplying the current they are sharing. The current they shared is this current they were receiving, 3.475. So here we get 1.39 milliamps. So this becomes 1.39 milliamps. Now, if the current that went towards, that passed through the 3 kilo ohms here is not 1 point, that was, 1.525, 1.525 milliamps. And the current that went down is 1.39. Then how much current passed through this line coming this side? So that is where we're going now. But here you have to say that we can even obtain the current that went towards the 10 kilo, but not very important. Instead, we can add these two to get the current that approached their junction. So how much current will be going that side when you add those two? What's that? 2.915 milliamps. Okay, so why do we need that one? Let's get the circuit just before that one. So the one we are on is this one. So just before it, we have this one, which is the starting point. So this is our final one. Okay, so just the key ones. So this one here through the 3, we saw that was 1.525. Coming towards the 15, 1.39. Now here, this is why I was saying it was important for us to understand how much current was shared at this point to get the 1.525 and the 1.39. And we were able to get the current that is approaching the junction here to be 2.915. That was 2.915 milliamps. So with this in mind, notice that we are now done, because the 2.915 here, according to this is the current that is coming from this source. That's the current that comes to pass through the 10. That's the current that comes to be shared this side. So when it reaches this point, you end up with 1.52 going that side, 1.39 going down. When it reaches here, splits up, we get what we had there and what comes down here. So this is where it is all coming from. Any questions? Looks like we're okay.
Right now, I can't remember to do this.
Now, okay. Yeah, when you look at how long it took us to do the first one and this one, you can think that way. But here I'm explaining as well. So with the explanation, of course, there's always those delays. But when I'm working out source transformation in just solving on my own, it doesn't take that long. Source transformation is more straightforward than Thevenin, than Norton, than those other mesh analysis. Source transformation takes less time. So at this point, we now know the current that is coming from the 50-volt source. So we can now easily get the power developed by that source. So the power developed by this source will be equal to voltage times current there. The voltage supplied is 50 volts. The current supplied, it's 2.915 milli. So this means by 10 to the power minus 3 amps. Or you can just multiply the 50 and this, the answer will be in milliwatts. So what will be 50 by 2.915? So 145.75 milliwatts, or times 10 to the power minus 3. So this becomes the power developed by that source.